Greetings, everyone. Today we're going to explore factoring polynomials to find real number solutions. So what we're going to do is we're going to take that last lesson of factoring, but now we're going to have an equal sign and we want to find our answer. By finding real number solutions, that means we're not going to run into anything imaginary in this unit. So please take out your notebooks and take notes where you see the little pencil on the slide, and we're going to go through some examples together. Again, just a reminder, to use factoring to find solutions to polynomial equations, we're going to continue to use greatest common factor, grouping, AC method, and difference of squares. Take a moment to jot down this first example. First, we want to check and make sure that our equation is in standard form. We want to make sure that we don't have a GCF. So if I take a look, the leading coefficient's 1, so I don't have a number I can divide out, and the 48 does not have an x, so I do not have a GCF. Because I have 4 terms, I'm going to start by using grouping. So as always, pair up the first 2 and the last 2. The GCF of my first parentheses is x squared. That leaves me with an x minus 3. On my second set of parentheses, just based on the signs, I can already tell I'm going to need to take out a negative. And I first want to check to see if 16 divides out evenly, and it does. So that's going to leave me with an x and a negative 3. Still all equal to 0. We ended up with the same factor twice, so if I divide that out, remaining I have x squared minus 16. Still all equal to 0. So here's what's new. We have to continue factoring. This second parenthesis is difference of squares because I can square root both sides and it has a subtraction sign. So let's bring down our first factor. But now that second factor breaks apart. The square root of x squared is x. The square root of 16 equals 4. And we have a plus or minus when we use difference of squares. Now everything is factored completely, so I can set each factor equal to 0, and I can solve. Now, you don't have to show this step. I understand that these factors are easy to see. So in the end, what I absolutely need to see, though, is that x equals 3, negative 4, and positive 4. If you want to write it as 3 plus and minus 4, that also works. As always, you can check your answers. If I take 3 and plug it in, I should get 0. If I plug in 4, I should get 0. If I plug in negative 4, I should get 0. Let's take a look at another example. Take a moment to jot this one down. First step is to make sure it's in standard form. Second, I want to see if I have a GCF. And I do. In this case, I know I can divide out a 2, and I can divide out an x cubed. When I divide that out, I have remaining an x squared, a negative sign, and 9. I don't need an x cubed there, so we'll close that off, still all equal to 0. Now I have 2 terms, and again I have difference of squares because these are both perfect squares and a subtraction sign. What you'll notice, to be honest, is in this unit, we're going to do difference of squares a lot, so just get used to looking for it every time. We have our GCF out front. Difference of squares breaks up. X squared square rooted is x. 9 square rooted is 3. Opposite signs. We could test this. If we were to FOIL x plus 3 and x minus 3 or multiply them, we'd end up back at x squared minus 9. So that's one way we know we're right. I've completed all of my factoring. So now I can take each factor and set it equal to 0. In this case, if I divide by 2, I'm still at 0. If I cubed root, I'm still at 0. So my GCF gives me the answer of 0. I end up with x equals -3 for my second factor and +3 for my third factor. Again, I can check these answers by plugging them in. Take a moment to jot down this example 3. First, make sure it's in standard form. Second, we want to check for a GCF, and in this case, I can divide out an x. That leaves me with an x squared, a -4x, and a -12, equal to 0. I have 3 terms. For 3 terms, I want to use the AC method. What you'll notice here, though, is I have a leading coefficient of 1. So remember, there's the shorter way to factor. If you still need the x, first times last is -12, inner is -4. Factors of 12 that can get me to 4. In this case, 6 and 2. I have to watch my signs though. It's going to have to be a -6. So let's check my answer. -6 times 2 is -12. -6 plus 2 is -4. Remember what this means is, because my leading coefficient is 1, those factors jump right into the parentheses. I can skip those middle steps. I'll prove it using those middle steps, but again, you don't need to do it when the leading coefficient is 1. So my middle term would be a -6x and a +2x. I would group. I'd have an x with an x minus 6, and I'd have a +2 with an x minus 6, which would get me to the x minus 6 and the x plus 2. So again, those middle steps with the leading coefficient of 1, you guys, you don't need to show it all. If it helps you to do the same process every time, go for it. Just know there's a quicker way. Now I have this factored, I've brought down my GCF, still all equal to 0. Set each factor equal to 0 and solve. So I end up with x equals 0, 6, and -2. Again, you can take some time to plug that in to check your answers. Take a moment to jot down this example 4. First thing we need to check is this in standard form? And for the first time, it isn't, which means I need to move that 14x cubed over to the other side, and it's going to end up going in the middle if I want it to be in standard form. So my actual equation that I'm going to use is 2x to the 5th minus 14x cubed plus 24x equals 0. Next, I want to check for a GCF, and I can divide out a 2x on this one. That leaves me with x to the 4th minus 7x squared plus the 12. In this case, I have 3 terms in the middle. Therefore, I'm going to use AC method, but again, my leading coefficient is 1, so I can jump ahead a little bit. First times last is 12, middle is -7. So I need 2 terms that multiply to get 12, but add to get 7. I'm going to use 4 and 3, but they both have to be negative. -4 times -3 is +12. -4 plus -3 is -7. So I'm going to jump ahead and skip those middle steps. But what I have to be careful of is instead of x and x, it's actually x squared due to these exponents right here. And then I've got a -4 and a -3. Alrighty, so next I can still factor. Again, like I said, keep an eye out for those difference of squares because x squared is a perfect square, 4 is a perfect square, and we have a minus sign. So all three elements are there. So let's break that down. That becomes an x plus 2 and an x minus 2. As for the x squared minus 3, that is not a perfect square, so we actually have to leave that one the way it is. But now I need to solve. Set each factor equal to 0. Now the first few are pretty straightforward. We're going to end up with x equals 0, negative 2, positive 2. But then here I got to do a little bit of work. If I add 3 to the other side, I end up with x squared equals 3. What's the opposite of squaring again? You got it, square root. So to get x by itself, I end up with positive and negative square root of 3. Don't forget your plus or minus when you square root both sides. Remember that little hint. I haven't brought it up in a while, but the degree of your polynomial states how many solutions you should have. I have a degree of 5 and I have 1, 2, 3, 4, 5 solutions. That's a good helpful tip for remembering your plus and minus. So to summarize, remember always put the polynomial in standard form. Always factor it completely. So that very often means don't forget difference of squares. Set each factor equal to 0. Solve for the variable. And don't forget, your degree should provide you with how many solutions you end up with. So use that as sort of a self-check, or at the end of your whole worksheet, look through and make sure that's true. Work on the example problems provided to you, and if you have any questions, let me know, and we'll see you next time.